section, that is the overall depth of the section. Small b, that is the thickness of the web. Small d is the depth of web. Now, the shear stress at any section which has been given by definitely by a fundamental equation, tau is equal to Fa y bar by Ib. Now, in this case, the shear stress distribution in the web and the shear stress distribution in the flange are to be calculated separately. Why? That we have understood when we are going to solve this particular problem. But right now you have to think, for I section there are three individual rectangles. Top flange acts as a rectangle, central rectangle is a web, and the bottom flange is a third rectangle. And we have to solve a problem by using a fundamental equation, tau is equal to Fa y bar by Ib. So now, first one, shear stress distribution in the flange. Consider a section at a distance y from the neutral axis in the flange. Refer the figure. Consider one layer. Right now let us consider layer EF. That layer which is in the flange section, which is at distance y from the neutral axis, and this is the shaded area. That area we have to count in the formula of Fa y bar by Ib. Now, here the width of the section is capital B, and the shaded area of the flange is given by B into D by 2 minus Y. Let us be understood on this table top. The given section, which is of I section, this is my neutral axis, as the given section is a symmetrical neutral axis at the center, and hence this available depth is d by 2, capital D by 2 from the top, which is same as small d by 2 from the bottom. Small d by 2, this is also small d by 2. Now what we did, we have considering this one of the layer EF, and we have to find out this area of this section. Available width is B. This is my Y value. So available depth for this strip or area is nothing but D minus 2 Y. D by 2 minus Y. So what is the area? Width multiplied by this thickness. The same thing which has been taken care over here on this PPT. Let us go ahead next one. Now, distance of the CG of the shaded area from neutral axis is given by as y bar, which is equal to y plus half of d by 2 minus y. I will repeat this one word, distance of the CG of the shaded area from the neutral axis, that is my y bar, means this is the CG of the area and this is my y bar. This y bar which has been given by y plus half of the depth. Half of the depth is nothing but the half of this. So y plus half of bracket d by 2 minus y. This is nothing but y bar. which is shown over here. So by simplifying this, we can achieve y bar as half of bracket d by 2 plus y. By simplifying this, we can achieve this one. Very simple numerical is there. Now, hence, shear stress in the flange becomes, as we know the equation tau is equal to Fa y bar by Ib. By putting all these values in this particular equation, F is as it is, A we know, B bracket d by 2 minus y bar which is already been known to us, half of d by 2 plus y divided by Ib. By simplifying this, we achieve F divided by 2I bracket d square by 4 minus y square. Very clearly visualize that tau is directly or inversely proportional to the y square in terms of minus sign, directly proportional to the y square. With the minus sign, it means that the variation of shear stress with respect to y in the flange is of parabolic nature. It is also clear from this equation that as the y increases, shear stress decreases. So, for the upper edge of the flange, where y is equal to d by 2, refer the figure on this tabletop very clearly that y is the distance from neutral axis to the layer. So, if I want to find out the value of shear stress on the topmost layer, I have to take y is equal to capital D by 2. And if I want to find out the variation of shear stress at this layer, that is the bottom of the top flange, then I have to take y is equal to small d by 2. So, the first one, if we take y is equal to capital D by 2 and put this value, the shear stress values comes as 0. It means that the shear stress variation at the topmost fiber of the I section is 0. While for the lower edge of the flange, where y is equal to d by 2, as we discussed on this tabletop, y is equal to small d by 2, by putting this value, we can achieve tau is equal to f by 2I bracket capital D square by 4 minus small d square by 4. 4 term is the out of the bracket. Then we got it f by 8I bracket capital D square minus small d square. Give it number 1 equation. This is the value of shear stress at the bottom of the top flange. Now, let us come to the next picture. The shear stress distribution in the web. What we did? We did the first part, the shear stress distribution on the top of flange. As we go to the second part, what will be the behavior of shear stress? What is the variation of shear stress under the web conditions? Now, please on this PPT, consider a section at a distance y from the neutral axis in the web as shown in the figure. Please refer the figure. I have taken one section EF at distance y from the neutral axis. Width of the section, because it is nothing but the width of the web, B. Here AY bar is divided into the two parts. Yes, interesting point. If you are referring the figure, AY bar divided into two parts. AY bar for the flange part, AY bar is sum of the web part. So, AY bar is equal to moment of the flange area about neutral axis plus moment of the shaded area of the web about neutral axis. Now, let us plot the same thing over here on this tabletop. What is this? Now, here I have taken a layer EF over here. So, EF is over here. This is my case. Second case, what is the variation of shear stress on this wave portion? This y distance is from here. This is the previous case. This is y distance from the neutral axis. So what is the two parts? The first is the ay bar for this flange. Second is ay bar for this web, sum of the web portion. Now refer over here. For the first portion, a into y bar, capital B bracket, small d, capital D by 2 minus small d by 2 into half of d by 2, capital D by 2 plus small d by 2. This is ay bar for the moment of the flange area about neutral axis. Let us be understood over here on this tabletop. Now, on this tabletop, please. Here, this is my first part, the first rectangle, this one, where available thickness is nothing but capital D by 2 minus small d by 2. So, the area with us is this multiply by this is the area, multiply by y bar. Y bar is nothing but the CG is over here. CG is over here. So distance from this to this, it is nothing but d by 2 plus half of this, d by 2 plus half of this depth. The same thing we did over here. Refer. This is the area, clearly B bracket capital D by 2 minus small d by 2 into y bar, and this y bar, if we are simplifying, let us be simplify over here on this tabletop. For the first rectangular portion, y bar is equal to small d by 2 plus the half of this, that is half of d by 2 minus small d by 2, and by simplifying this we can achieve half of d by 2 plus small d by 2, because this is plus sign and this is of minus sign. By solving this we can achieve this. Same thing we had been kept over here on this PPT. Refer. Now next, another part, moment of the shaded area of the web about neutral axis. Here the moment of the shaded of web area, this is the width multiply by the available depth for the shaded area. So if you want, please refer this figure on this tabletop. Clearly this is the another portion, web portion. B is the width available, depth available is this one, and this depth is nothing but d by 2 minus y, because this is y, this is d by 2. So d by 2 minus y is the available depth. Now this is the area. Now I want to find out a y bar. Y bar is nothing but the half of d by 2 plus y. How this can be arrived? Please see over here. Now CG is over here. I want to find out this as a y bar. It is nothing but y bar is equal to half of d by 2 minus y, it is this distance, plus y. By simplifying this is equal to half of d by 2 plus y. This is the y bar for the second area. The same thing which has been kept over here on this PPT, if you are referring this PPT. And by simplifying this, we can achieve ay bar is equal to capital B divided by 8 bracket capital D square minus small d square plus b by 2 is out of the bracket small d square by 4 minus y square. Now, hence, the shear stress in the web becomes as F A y bar by I b, and F and I b if we take as a common out of the bracket A y bar, that is of bracket capital B by 8 bracket capital D square minus small d square plus small b by 2 bracket d square by 4 minus y square. From the above equation, it is clear that the variation of tau, which is directly proportional with the minus y square, that is the parabolic nature, also with the increase of y, r decreases, tau value is decreases. As y increases, the tau is decreases. Hence, at the neutral axis, y is 0, the shear stress is maximum. So, if we are putting y is equal to 0, we can achieve tau maximum is equal to F by IB bracket capital B by 8 another bracket capital D square minus small d square plus small bd square by 8. Now, at the junction of the top of the web and the bottom of the flange, where y is equal to d by 2, let us be understood this one. What is the intention? We have already been found out the variation of shear stress at the bottom of the flange with the considering the only the flange area. But now if we are taking the consideration of the web also, then what will be the variation of the shear stress at the junction on the top of the web? We have to put y is equal to d by 2 small d by 2, and by putting the small d by 2 y is equal to that value, we can achieve tau is equal to f into capital B bracket capital D square minus small d square divided by 8 into IB, give it number 2 equation. Now, please visualize both the equations carefully. The shear stress distribution on the web and the flange is shown in the figure clearly. Now, the shear stress at the junction of the flange and the web changes abruptly, because if you are referring equation number 1,